Good morning, everybody. Okay. Oh, hope I got a pencil out. Okay, so we're going to start today by kind of coming back to the slide on mass spectrometry that we were ending with last time, and get into things like atomic weights, and then get into the periodic table, and maybe do a couple demonstrations this morning. So the mass spectrometer shown here, there's not a whole lot about this specific instrument that you need to know, other than this is how we can look at different elements to figure out what isotopes exist naturally for that particular element. So like chlorine exists as chlorine 35 and chlorine 37 in a natural sample in about a 3-to-1 ratio. Again, not worth memorizing that particular detail, but you might imagine doing this for hydrogen, where hydrogen's mostly hydrogen 1, a tiny bit of hydrogen 2. You might then look at things like carbon. We'll show it on the next slide. We're talking about it previously. Mostly carbon 12, a little bit of carbon 13, a very, very small trace of carbon 14. And so these are the types of experiments that would be done to try to determine those different isotopes, what they are, and then to quantify what their specific atomic weights are. The way this technique works is you just put a charge on these ions. Like imagine putting a positive charge. They have a small but different mass from each other, and by the difference of mass to charge, they bend to a different extent with the magnet that they kind of flow through, and then that allows them to bend a different way, a different amount, and then hit a detector. So you kind of vary the magnetic field, and then you kind of count the ions that are hitting the detector to determine, how many ions there are, and then what the specific mass to charge ratio is for that ion. And so for something like carbon, you can see some of the data down here that carbon 12 has this mass of exactly 12 AMU. We'll talk about why it's exactly 12 AMU in just a moment. 98.93% of a natural sample of carbon is carbon 12. Almost the remainder, in fact, if you do the math, the remainder is carbon 13 with, like we mentioned before, the amount of carbon 14 in a natural sample is so small, it's like less than 10 to the minus 10%. So a very, very tiny trace of carbon 14. But about 1.07% is carbon 13, which has this particular mass in AMU. So about 1 neutron more, or precisely 1 neutron more, but the mass is about 1 neutron more than that of carbon 12. Okay, so let's talk about this atomic mass unit scale. Now, on one hand, we can define a conversion factor that relates AMUs to grams, but let's talk a little bit about how the scale itself was devised. So the way this scale is kind of set up is that one single carbon 12 atom in this scale is defined to have a mass of 12 AMU, and this is by definition. So this is like a defined quantity, and this therefore would be an exact number because we're setting a scale based off of this mass. And so what you then might do is say, well, how does that help us relate something like the mass of an atom into maybe some ordinary unit like grams? We might want to know what's the conversion factor between AMU and grams. Well, let's then extend this kind of thought of carbon to kind of think about the mole unit. Now, the mole itself isn't introduced in the book until the next chapter, in chapter 3, so we might see kind of this derivation or this thought again later, but 1 mole of carbon 12 would contain an Avogadro's number of carbon atoms. In fact, you probably know, or if you've seen this before, a mole of anything contains specifically the Avogadro's number of that thing. So a mole of carbon 12 would correspond to having 6.02214,179 times 10 to the 23 carbon 12 atoms. So if you had a mole of carbon and you can count this, and obviously we do this through an experiment, we find Avogadro's number precisely out to a bunch of digits. It's 6.02214,179. Now again, I wouldn't bother committing this to memory to that number of decimal places, and then also this is generally given on tests if you need Avogadro's number, so it's usually not something you have to remember. But then you could determine, well, what is the actual mass of the collection of this number of atoms, and it turns out to be 12 grams. So this turns out to be equal to that this collection of carbon atoms here is equal to 12.0000001 more 0 grams. It's like 9 total sig figs. So this value here should have 9 sig figs. And then this here has 9 sig figs if you're counting the zeros. And so that collection of carbon atoms has been determined to have that mass of about 12 very precise grams. And so then you could say, or ask the question, well, what's the mass of one atom? You see, we know what the mass of Avogadro's number of atoms are. Well, why don't we just simply divide 12 by Avogadro's number? So if I do 12 divided by 6.02214,179 E23, I get that the mass of a single atom of carbon-12, so if I just simply divide both sides here by 6.02214,179 times 10 to the 23, and let me get rid of this sig fig counting. I don't need the sig fig count here. And so we're just dividing both sides by Avogadro's number. So then obviously that cancels. Then one carbon-12 atom has a mass of 1.993, or I'm going to write 1.9926 and then dot, dot, dot. I'm not going to write the rest. But, we'd be writing about 9 sig figs here if we wanted to be correct with our sig figs. But that's the mass of one single carbon atom in grams. Now, if you're with me so far, so we had a collection of carbon-12 atoms, had a mass of 12 grams. We then figured out the mass of one single carbon-12 atom in grams. But then we also said we defined in the AMU scale that carbon-12 atom has a mass of 12 AMU. So this 12 AMU exact defined quantity is therefore equal to the actual mass to conversion factor to grams, would just be that it would be that 1.9926 dot dot times 10 to the minus 23 grams is equal to 12 AMU. That's like defining our conversion between AMU and that mass scale in grams. So we're specifically choosing carbon here for this example to define the AMU scale to set its mass of carbon-12 to exactly 12 AMU. But we're doing so because we're taking the nearly exact 12-gram sample of carbon-12, counting the number of atoms in that sample through other means, not physically counting. It would take a long time to count up to 10 to the 23. But then we're figuring out the mass of one single carbon-12 atom so that then we can say 12 AMU is equal to that number of grams. Now let's take 12 AMU, divide by 12, and that number of grams and divide by 12, because that'll give us the 1 AMU to gram conversion. We probably don't want a conversion factor that says 12 AMU is this number of grams. That's a weird way to give a conversion factor. So let's just divide both sides of that conversion by 12. That gets rid of the 12. So 1 AMU would be equal to 1.6605 dot, 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 times 10 to the minus 24 grams. So weird derivation, but hopefully what you're seeing is just the AMU to gram is just a direct conversion. There's a conversion between the AMU scale and the gram scale. And 1 AMU is a tremendously small amount of mass. One single carbon-12 atom has a very, very small mass. But we tend not to work with single atoms. We're going to work with moles or gram quantities where we work with massive collections, on the order of 10 to the 23 atoms at a time of atoms are the type of samples we're going to be working with. Now let's do one more thought. That would be figure out how many grams there are in an AMU. So if you know there's like 1,000 centimeters in a meter, then you can also say that 1 centimeter is 10 to the minus 2 meter, right? So you can give the conversion factor for any conversion factor both ways. Let's just divide both sides. Let's call this x here, just so I can divide both sides by that 1.6605 times 10 to the minus 24. In other words, let's just invert that 1.6605 times 10 to the minus 24 number. I just do 1 over, and then I get Avogadro's number back. So if we want to give the conversion factor and say how many AMU are in 1 gram, so 1 gram would equal or contain an Avogadro's number of AMU. I think that's interesting to see that if you think of your AMU to gram conversion, that 5 minutes ago, you had no concept probably of how AMU and grams could be related to each other. But what you can see is we just take the mass of the actual carbon-12 atom, set it equal to 12 AMU, get our AMU to gram conversion, and then kind of do an inversion to see that we also have an Avogadro's number of AMU in 1 gram. So 1 gram contains a tremendous number, this Avogadro's number of AMU. So I think it's kind of neat that you see the same number come out, but it's also very intentional that you see the same number come out. What this will allow us to do is to start thinking about an atomic weight of like an atom, like let's say carbon. You can say carbon's atomic weight is 12 AMU per atom, or it's 12 grams per mole. That those will be synonymous units with each other. So we can think of, for carbon-12 as an example, you could say it's either 12 AMU per atom is its atomic weight, or you can say it's 12 grams per mole. And again, the mole, we'll talk about it more later. We're just kind of giving a rough introduction to the mole unit today, but a mole of anything is just that Avogadro's number of particles. So a mole of carbon, Avogadro's number of carbon atoms. If you had a mole of, say, CH4 of methane, you'd have an Avogadro's number of the methane molecule, so of the molecules of methane. Okay, now let's circle back to kind of what we're really going to try to do in chapter 2 is just understand atomic weights a little bit better. So hopefully we understand the atomic mass unit scale, that it's an AMU scale that relates to the number of grams, and it's a really small conversion. And then the average atomic weight of an element, what we probably want to know is when you look at an element on the periodic table and you see all those numbers listed underneath, like carbon, it says 12.011 on the periodic table in the room, we probably want to understand, well, why does it say 12.011? Why doesn't it say 12? Well, for carbon and all the other elements, we have to think, well, what's the sort of weighting of all possible isotopes that element exists as naturally in a sample we're going to encounter and use in the laboratory? So the average atomic weight will be equal to the sum of the individual atomic weights of the isotopes that a given element exists as naturally times the fraction of that isotope that it exists. So what's the fractional sort of existence of that isotope? What's its atomic weight? And then we're going to sum these up over all possible isotopes for a given element. Summation signs always kind of take us back or forward in math to maybe something we've seen or haven't seen in a while or maybe haven't seen yet. But we're just summing over all possible isotopes, taking their individual atomic weights times their natural abundances. Okay, now let's do an example with carbon so you can see this in action to see that this equation, though complicated maybe in nature, is pretty simple to use. For carbon, again, 98.93% carbon-12, and then 1.07% carbon-13 with their masses given here. So if I want to calculate the average atomic weight for carbon, I'm going to take the sum of those two isotopes. So I'm going to take carbon-12, 12 AMU. Now, again, I'm going to write exact so I can hopefully remember that's an exact number of sig figs, not 2. That's like an infinite number of significant figures by definition of the scale. I'm going to multiply this by 0.9893. I'm going to take the percentage, 98.93, and just make it a fraction. So the fraction here would be 0.9893. The fraction of the carbon-13 would be 0.0107. So I'm thinking about their fractional abundances instead of their percent abundances. And then I'm going to add to that 13.0034 AMU times 0.0107. So if I do 12 times 0.9893, I get 11.8716. And again, I'm going to keep 4 sig figs here, not 2, because I'm going to look at this as being 4 sig figs. I'm multiplying, so I'm applying the multiplication rule. And then this, again, it looks like 2. You might think it's 2 sig figs, but because it's exactly 12 AMU, that's why it would be an infinite number of sig figs. So this number of sig figs in this context here is infinite. So infinite sig figs times 4 sig figs should be rounded to 4 sig figs. And then 13 times, or 13.0034, the atomic weight of the other isotope, and then times its abundance, which is much lower. That works out to 0.139, and then 1. Sometimes it's good to carry an extra digit on with a problem, like to carry an extra sig fig after the last digit of significance. Like I mentioned last time, for test problems, you don't necessarily have to overthink this too much. You can just go, we could have rounded this to 0.139, it rounded the other one to 11.87, or we can keep these digits along for the next step of the calculation, then round once at the very end. But the key would be just kind of noting the 8.7 should end in the 7, the 9 should end in the 9, and then we're going to round, when we add these up, to the higher decimal place, to that hundredths place. So if I do 11.8716 plus the result of this calculation, I'm going to get 12.0107, so I'm going to round to 12.01. So from this work here, we'd say the average atomic weight of carbon is 12.01. Now that's AMU or grams per mole. Again, we'll do more calculations with the mole unit in the next chapter, but you can kind of get a sense here that anytime you have an atomic weight in AMU, it's AMU per single atom of that substance. Now, to me, that's confusing because the per atom here is like the average atom of carbon, which is a weird concept for thinking of a single atom. So when you see 12.01, it's the average atomic weight of an average carbon atom, where it's 99% this one, about 1% the other, so a little bit higher than 12. But when you start thinking of having an Avogadro's number, I think of atoms, you can start to think, well, about 99% of them are going to be carbon 12, 1% of them carbon 13, and then the average of the masses of those atoms ends up being about 12.01. If we were to think back about chlorine in the previous example, where we saw it was about 3 to 1, 35 to 37. Now, if you think the atomic weight is about 35 AMU for the chlorine 35, it's about 37 AMU for chlorine 37. The average atomic weight of chlorine is probably about a quarter of the way between the two. So if you look at the atomic weight of chlorine, it's 35.4537 on that periodic table. So about 35.5. So you see it's a little closer towards 37 because it has a higher abundance in that heavier isotope. Carbon 13's abundance is really small, so it doesn't really change the mass of carbon 12 to be much higher, so it's only about 12.01. Now lastly, you might wonder, well, how do you know that carbon's 12.011 here when it's 12.01 in our example by sig fig rules? Well, we just have to get more precise numbers. So if we use more precise data or actually look at a sample and analyze it, we can get more precise data, and the periodic table showing that data. Within a context of an example, we may not have that extra information. So that's the atomic weight scale. That helps us hopefully understand, when we look at a given element, like for example, let's look at iodine for a minute. Iodine's 126.90447, but that's the average weight of all the possible isotopes that exist for the element iodine. Well, some elements exist as only one isotope. It's possible. Iodine actually happens to be one of those, where iodine 127 is about the only natural occurring isotope of iodine, and then you can know that the isotopic mass of iodine 127 is therefore about 126.90447, when you know it just contains that one particular isotope. So you'll see some examples of calculating atomic weights given some data. And another popular problem you'll see, there's a couple examples of this on the daily quizzes if you see them, where if an element has like two isotopes, we could do a lot of like word and like math problems where we maybe give you the average atomic weight, maybe the individual atomic weights, and you have to work out the percent composition. So you'll see some examples of that, of trying to solve for percent compositions of isotopes, given their average atomic weight and some other information. So you'll see a few math problems that kind of relate those quantities. We'll probably work one of those into like the review later when we get towards closer towards midterm 1. Okay, so let's move away from thinking about the actual calculation of atomic weights into some properties of different groups of elements. So I think we know one thing that's, I want to go back, but if I go back, the recording is very strange. So if we look at this periodic table here, I think we kind of come to know that like the first group, the alkali metals share some properties together. The alkaline elements share some properties together. We probably know all the noble gases are gases at room temperature, like helium, neon, argon, krypton. That entire group of elements share that property. The halogens share some properties too. Let's take a look at a few different classes of compounds that share some properties and see what we can figure out today. And so these here are sort of the halogens. So this is bromine. Bromine is that liquid element. One of the two liquid elements, mercury being the other. You can see some liquid in the bottom of the flask. You can also see that there must be a high vapor pressure of bromine, because we see the BR2 like vapors above the liquid. And then this is, I think this is chlorine. I don't think we have chlorine here. So this will be chlorine. Gas sample is no liquid or solid at the bottom of the container. And then iodine here. Here's an iodine. You can see the solid crystals again must have a relatively high vapor pressure, because we can see the iodine vapors, the pinkish color above the solution. And so what the halogens share a property of isn't necessarily the physical state, because you can see gas, liquid, solids, so they're not sharing that particular property. But they do share the property of existing inside atomic molecules, so CO2, Br2, I2, and just naturally in their different physical states. This here is another sample of bromine, but what this allows me to do is take something cold like liquid nitrogen, where I can try to freeze out the bromine. So I can hopefully just put this into the liquid nitrogen, and then over time, it might take a minute or a few seconds to show this, the vapors are going to condense back into the liquid and then the solid form, to freeze out the bromine. And so I think you can see, I don't know if you can see it, I think I can see the brown color kind of starting to dissipate. Maybe if we compare over here, you can see that it's getting lighter. And so that's just because we're forming a Br2 solid, and those vapors are just being pulled back into the vapor phase. This is just like taking water vapor back to liquid and then into solid form. It kind of stains the glass, so we want to see the color completely dissipate. And so that's frozen bromine. Here. And then over time, it'll go back to looking like what it was before. This one here should be fun. This is where I can start a fire. Okay. So what we're going to do this one is see some of the periodic properties of like sodium metal reacting with water. So let me fill these up with a little bit of water. So who has seen the reaction of like sodium with water? Has anybody seen this in class? This is like a fairly common thing that you may have seen before. This one's a fun one. Potassium will be exciting. Some of the ones aren't super exciting. They usually have water prepared, so I may not do the ones that aren't so exciting. But let's look at sodium into water. So I'm going to take, now sodium metal, what you do is you keep it in like a mineral oil, otherwise it will oxidize on the surface from reacting with the moisture and air. So just going to put a piece of sodium. And what it's doing is it's reacting with water. We'll talk, well, we cut the reaction on the top of the side. I used to talk about the reaction, but sodium is reacting with water, producing hydrogen. The hydrogen is igniting due to the exothermic nature of the reaction. And so the heat of the reaction that's taking place is actually igniting the hydrogen as it reacts. And so that's sodium reacting with water. Now the fun one, I'm going to do it with a bigger flask, because this one can get even crazier than that, is potassium and water. In fact, there's another thing I could have done. They gave me some of this indicative solution, like an acid base indicator to show that we're making a base here. So if this turns pink, we'll show that we created a base during the course of the reaction. So I'll add some of that in this solution here. As we start neutral, we don't see the color yet. So if we produce a base, we're making sodium hydroxide, the sodium reacting with water, hydrogen being the byproduct. Not worth memorizing that those are the products of those reactions or anything, but just trying to think of some different group properties and group tricks. So we would probably expect potassium to react similarly. It will react similarly, it'll just be a little bit more violent. Like so again, it's a mineral oil. Some big pieces in here too. They're really I like how it just like instantly ignites. Okay. So it's pretty similar to sodium sulfates. So it's pretty much the same reaction, just a lot faster. We'll talk in chapter 7. It's really because the electron is a little further away from the potassium nucleus. It's easier for it to lose that electron and get it off of the solution. Sodium's a little closer, a little harder, but still easy. Still gets it off. Just takes a little more. So that's potassium. Sometimes you put potassium, it has a tendency to fly out. And if it does, it can light the fire. So that's always a fun possibility. Okay, now one last thing. This is not all that exciting, but it's to take like the alkaline metal and put it in water and see that it reacts differently. So let me just do some more. Let's put some magnesium. And I'll put a little of that indicator here too. So magnesium is a little different because it's not actually stored over a mineral oil. It's just in its powder form. So I'll just put some magnesium in and see that it just reacts in fundamentally not the same way as the alkali metals. So it doesn't really do much of anything. It will eventually dissolve, and when it does dissolve, maybe it's calcium. One of them reacts, you can see a little pink color coming out of the metal as it's slowly dissolving. So maybe it's magnesium doesn't dissolve. Let me try a little piece of calcium. So the calcium, can you see the little pink color of the indicator turn color? So the calcium is reacting, just not as fast as the alkali metals. And certainly the magnesium doesn't appear to be reacting at all. So you can see a little bit of reactivity with the calcium. We do see that group trend kind of as we go top to bottom. We have a little bit of an increase in that rate of reaction with calcium compared to magnesium, just like potassium reacting faster than sodium. Okay, so hopefully what we're seeing here is that we get some group trends. Alkali metals have a trend together. So one of the trends of the alkali metals is that these are forming +1 ions in water or in solution. So they form sodium plus, potassium plus, rubidium plus, et cetera, down that first group of the periodic table. You might have kind of thought that the reason why they form the +1 is they're going to that noble gas count of electrons. If we think of counts of electrons, for example, sodium would have 11 protons, 11 electrons. If we lose an electron, we would go to 10 electrons. So sodium plus would have 11 protons. Again, remember from last time, we don't change the proton count for ions, we change the electron count. We lose 1 electron to go to sodium plus. So sodium in its +1 form, let me even rewrite that, it's a little sloppy. So sodium with a positive charge would have 11 protons, 10 electrons. If you look at neon as a noble gas, neon, the noble gas, element number 10, so therefore has 10 protons, equal number of electrons, since it's neutral, 10 electrons. So that noble gas count of electrons is that stable count. That's ultimately why the noble gases have their stabilities, because they have that right count of electrons, or they have the right balance of positive, negative charge, where they don't need to share electrons, gain or lose electrons to form a stable count. So our noble gases, these exist as monoatomic gases. Monoatomic gases because they're stable as a single atom, where the other elements in the periodic table need to do something, bond with something else, or lose or gain an electron to gain some stability. Halogens, we saw that they share the property of forming these diatomic molecules. And they also tend to form -1 charged ions, so they'll also form minus ions. So they'll form Cl minus, F minus, Br minus, I minus, commonly with other elements in ionic compounds. So like sodium chloride, sodium bromide, sodium iodide are all compounds that exist. The chalcogens are the name of the oxygen group. These share a couple properties of forming -2 ions. We do get a variety of properties for some elements or some groups where you go from having like a non-metal element like oxygen, sulfur, selenium, and eventually as you go down the periodic table, you eventually get to the metalloid elements, which are sharing the properties of metals and non-metals. So our metalloids kind of zigzag. So like the silicon, phosphorus, germanium, arsenic, not really labeled on this periodic table. I think they're labeled on the one in the notes. But the elements that kind of zigzag down the periodic table, those are going to have properties kind of like a metal. So metals tend to have really high melting points and boiling points. So the metalloids usually share that property. But then they usually don't have the same conductive properties. They usually don't conduct heat and electricity in the same way that metals do. And they usually have some variable properties that make them useful for like semiconductors. So metalloids, very interesting in their properties, but they're not kind of like you think of the nonmetals, which have really low melting points and boiling points. When we think of things like O2, F2, neon, those are gases at room temperature, so really low melting points and boiling points, obviously. And as you get bigger, as you get to like sulfur, it's a solid, where oxygen's a gas at room temperature. So as you gain some size in your metallic, your non-metal elements, they can gain some melting points, they could increase in their melting point and boiling point trends, but not to the point where they look like something like, say, carbon, which I think is a good thought of a metalloid compound, where it has a melting point of like 2,500 degrees C in diamond form. So really high melting points and boiling points, but not anything like a metal. So nothing like a metal at all in the way you think of its behavior. The alkaline metals, these form +2 ions. So that's one of the properties they share. Not really reactive with water, as we kind of saw. Not as reactive with water as the alkali metals. Now, the two things that, so for the elements that have to bond with other elements, like pretty much everything except the noble gases, the choices that the atoms have are to form some sort of bond with each other, like covalent bonds. That's common for molecular compounds. These are common for our non-metallic elements. So our non-metallic elements are those on the rightmost side of the periodic table and hydrogen. So our left side of the periodic table, all the black shaded elements, those are our metals at room temperature. And I think we continue the shading through some of the metalloid elements as well. But the metallic elements aren't going to form these type of molecular compounds. We're going to see that the metals tend to form ionic compounds with elements when they form compounds. So non-metallic elements will bond with each other to make molecular compounds. And so some simple examples of these could be that H2 bond and like hydrogen. This could be the F2 bond in something like fluorine. This could be the bonding in something like CH4. Now the actual sketching of Lewis structures, like if you're sketching, like the way I'm sketching H2, F2, if I were to make O2 with like a double bond for O2, these are topics from chapter 8. So we'll learn how to sketch Lewis structures. So I'm not going to give you a random formula here in chapter 2 and expect you to write and sketch a Lewis structure. That's a topic for later. But I think it's important for us to think that the important part here is this bond here, that these types of bonds that are connecting the atoms together are those molecular or covalent bonds, and that's what makes something be a molecular compound, is having those are shared electrons between the atoms that are connecting them together. So we get this with CH4. So CH4 has 4 single bonds with hydrogen. It actually has a shape. We talk about this shape in chapter 9 to think three-dimensionally. How does something like CH4 look? And then we can also represent things with like a ball and stick or like a space filling model. So we have different models for showing molecular shape. Again, you're not expected to be able to like put together or piece together what something should look like yet. We'll get through that as we get through chapters 8 and 9. What's important here is sort of recognizing that molecules have a molecular formula that's really important for understanding that compound. So we usually want to look at a molecular compound and talk about its molecular formula. So something like CH4 is what we want to know, is that's important for CH4. That's a collection of atoms in one molecule of CH4. Ethane is like C2H6. So this would be ethane. We'll see this in a few. We'll probably see this on Monday in terms of a category of naming hydrocarbons. But in terms of ethane, it's formula C2H6. Like one molecule of ethane would contain 2 carbon atoms and then would contain the 6 hydrogen atoms. Again, I'm not showing this so that you know how to sketch ethane per se, but just so that you can start to think that somehow a molecule of ethane has to contain 2 carbon atoms and 6 hydrogen atoms. Now, we can also talk about empirical formulas, and when we get into chapter 3, we'll talk about experimental data that can let us calculate an empirical formula. You might remember those percent composition problems, something like 85% carbon, 15% H, what's the empirical formula? You might remember those problems. We'll see those in the next chapter. An empirical formula doesn't really tell us much. It's not all that useful of information. This is the simplest ratio. So the simplest ratio in C2H6 would be like CH3. But saying the empirical formula of ethane is CH3 doesn't really mean anything. Like if you had another formula of some other compound, let's say it was, let's say you had a compound that was C4, H12. Well, my brain shut off for a minute. But C4H12 would share the same empirical formula as C2H6, I think. Yeah. And so this would also have that same empirical formula of CH3. Now, there's virtually nothing that would be in common between those two compounds. If you had a sample of C2H6 and a sample of C4H12, they would have nothing in common with each other just because they had the same empirical formula. So there's really nothing noteworthy of sharing an empirical formula with a compound. Another example could be like you could have C2H2 be acetylene, or C6H6 be benzene. Now the properties of acetylene and benzene have nothing to do with each other. Just because they have the empirical formula, the same empirical formula of CH, means nothing really of consequence for those two compounds. So the only reason I think we bring up empirical formulas in this chapter is so that you can recognize the simplest ratio can be written. We can look at these two compounds and see that they have the same simplest ratio of just C1H1 or CH. But then later, we're going to do like an experiment, or from experimental data, we can find the empirical formula, and we'll have to do some other experiment to find the molecular formula. And the molecular formula is what you really want to know. That's the important one. So if you're looking at a molecule and saying, do I want to know its molecular formula or empirical, you want to know the molecular formula. Okay, so I've talked for a while. Let's take a break and do a sig fig problem. So why don't you guys try to work on a problem from chapter 1 just to review some sig figs. So give this one a try. We'll review it in a couple moments. So what do you guys think? A few of you might still be working, but anybody think it's A, B, C? That's the right answer. So C is the right answer. So when we look at 0.00015 times 54.6, only 2 sig figs here. So that one would be 0.0082 if we're writing the result of that calculation. And then plus 1.002, we line up the decimal places. We go to the higher quantity decimal place. We round to the thousandths place holder. So that would be 1.010. Now, the one thing that's always weird with these problems is that presumably different tools were used to measure those two length units. Then when you see these problems, you'll see units given, and you may not understand where these numbers came from, but just remember that the whole thought here is at 54.6, that there's about 0.1 meters of uncertainty in that number. That's really where the sig figs is coming from, is the uncertainty and that last digit being like at least 1. And then if you look at the 0.00015, that it's 0.00015 plus or minus 0.00001. That it's like that inherent uncertainty in the last digit in these numbers that's giving the sig figs their place and their role, and that's the sort of errors that we're tracking through using the decimal place, like looking for the decimal place to round to when we add and subtract, and looking and counting the sig figs when we multiply and divide. If you take a stats class, you'll see how to actually use these uncertainties and propagate them and calculate them in equation form, very carefully, so you can actually put a plus minus to your result. But here we're kind of doing that just by rule. So we're doing that behind the scenes, if you will, just by following the addition, subtraction, or multiplication, division, sig fig rules, and just trying to make sure we apply them sequentially when we do problems. Okay, so I think that's the last sig fig problem that's in the notes. There's a bunch in the daily quizzes. If you're still getting tripped up on some of those, check out those problems. The last part of chapter 2 is on naming a bunch of different categories of compounds. And so let's get into a few of these categories and start to think about how we can name things systematically by probably first trying to recognize what kind of compound we're naming so we can think about which sort of category it fits into and then name it for the role for that category. So the basic compounds we're going to learn how to name are ionic compounds. Let's start thinking of examples, because I think we know examples of all of these categories that will help us try to look at a compound, classify it as what it is, and then try to name it accordingly. NaCl is a really easy example of an ionic compound. So Na plus Cl minus, we have a picture of it on the next slide to kind of think about how NaCl looks in its solid form. So that would be an example of an ionic compound. So just something with a positive charge, something with a negative charge, usually metal, non-metal, or metal with a non-metal collection of atoms that we'll see. You might have seen something like a sulfate ion. Na2SO4 would also be an ionic compound. So we have the sodium ions, and then we have this sulfate molecular ion. So we'll talk about naming molecular ions too as we go. We can name acids, and you've probably encountered or seen acids in examples, or maybe used them in labs in high school. These could be things like hydrochloric acid, maybe nitric acid, maybe sulfuric acid. So maybe these are some acids you've seen in examples or maybe used in the laboratory before. And so acids we usually recognize as having usually some sort of ion that we recognize, like chloride, nitrate, sulfate, and then with H plus to neutralize the charge. And so we usually think of acids as containing H plus. Usually they start with H in their formula. Not always, but a lot of times you see H out front. So like HCl, HNO3, H2SO4. You might have seen like acetic acid is one that comes to mind, where sometimes the hydrogen's given last, but it's because we have the COOH group. If you've seen any organic chemistry, you know that that's like a carboxylic acid group. But sometimes we actually write this formula HC2H3O2, just so you can see the H out in front. So there's like two ways that we sometimes write acetic acid, maybe in more structural way, CH3COOH, or in this more like category of trying to put H out in front, HC2H3O2, where this is acetate. And then this form here, this is just acetate written out in a different way. And so acetic acid is the acetate ion in its acid form. Binary molecular compounds are just where you have binaries having two elements, and then it being molecular is a collection of non-metal elements. So this might be something like CO2 would be a binary molecular compound. We want to be able to name things like carbon monoxide different from carbon dioxide. So we want to make sure that we have a system for naming the compounds that can exist, like N2O versus NO2 versus NO. So there's all these different collections of of non-metallic elements that can exist in these binary compounds we want to be able to name. You've certainly encountered carbon dioxide, hopefully not carbon monoxide, because that's a odorless but very poisonous gas. So we like to just make sure we know how to name these things. And then we have some simple hydrocarbons like alkanes. 2 examples today already were methane and ethane are examples of alkanes. So these are just saturated hydrocarbons. That just means they don't have carbon-carbon double bonds in them. If you've seen things like ethylene or acetylene, things like that. So they only have single bonds, and then alcohols of these, methanol, CH3OH. So an alcohol we'll see is just where we replace a hydrogen in the alkane with the hydroxyl or the OH group, with the OH IO group. Sorry, you say IO. It's okay, it's early. It was kind of silly. We'll do one at the end of class because I hear there's some ball this weekend. Okay, so let's look a little bit finer tuned at these different compounds. That was just meant to be a quick little introduction to the categories so that we can hopefully start to recognize different categories of compounds. So our ionic compounds, we just have something like sodium loses an electron like we mentioned earlier, 11 protons, 11 electrons, loses an electron down to 10. Now, what if the electron goes over to chlorine, which is like 1 away from that noble gas count of electrons? If chlorine could pick up an electron, so chlorine goes from 17 protons, 17 electrons, picks up that extra electron to go to 18, and picks up that charge of minus. So we form sodium plus, sodium minus. They then have and can have a mutual attraction with each other, and then form a series or an array of atoms in like all 3 different dimensions where we have the alternating plus minus, plus minus, plus minus. So we kind of call this thing here a lattice, or a crystal lattice. And so the sodium chloride, once it forms, gets the benefit of that lattice energy, gets the benefit of the energy it would take to separate all those plus and minus attractive forces. We talk about actually quantifying and comparing different ionic compounds' lattice energies in chapter 8 later. So we'll see that topic kind of come back up. But when we think of ionic compounds, we usually think of them as being solids at room temperature because they have these strong forces of attraction holding those ions together. And then some of them we can put into water and they'll solubilize and they'll become surrounded by water. We'll talk about that in chapter 4. So chapter 4, we'll talk about sodium chloride and water. Each one of these ions, kind of one at a time, is plucked off by water and is surrounded by like a little water sphere. So we'll talk about aqueous dissolution reactions in chapter 4. But so we tend to think of ionic compounds in solid form, being solid at room temperature, or added to water. If they're soluble, they can dissolve. Some ionic compounds we'll see in chapter 4 don't dissolve. So we'll talk about that in chapter 4. Now here are some of the key ions of the different groups of elements of the periodic table. We were already talking about the alkalis being pluses. Hydrogen can also form a plus ion. The alkaline metals form +2 charges, magnesium 2+, calcium 2+. The first element, beryllium, tends not to form ionic compounds too commonly, so we don't see too many examples of beryllium salts, but we see salts of the larger alkaline metals. And then nitrogen, notice it's 3 away from the noble gas, so it forms a 3- ion. Oxygen's group forms the -2 charged ion commonly, so O2-, S2-. The halogen group forms F-, Cl-, Br-, I-, and then you also see hydrogen can go to minus as well and form a hydride ion. And so we like to be able to name these different ions so that we can understand how we can name compounds containing these ions within those types of compounds. And so let's try to piece together, or like maybe summarize it here, and then within the summary talk about how we can name or some of the sort of pieces of nomenclature here that we're picking up. So the lithium, sodium, potassium, rubidium, cesium, those are the alkali cations. If I said sodium cation, we're going to know that it's sodium plus. If I said magnesium cation, we're going to say, I know that's magnesium 2+. Like I don't have to say magnesium 2+ cation or magnesium 2. I don't have to tell you much about magnesium cation other than by magnesium, where it is in the periodic table, we'll know that that's magnesium 2+. So when we start naming compounds, let's name 2 already. NaCl, we know that's sodium chloride. But MgCl2 is not magnesium dichloride. It's not like magnesium 2 chloride. It's just magnesium chloride. We don't need to have any more fancy of a nomenclature system than magnesium followed by chloride. Like, I don't have to specify 2 chlorides because I know I'm going to get to 2 just because of the charge of sodium. It's going to need 2 chloride ions to balance out the charge. So because I have a 2 plus, I have to have 2 chlorides. Because I know magnesium can only form a +2, means I don't have to name this thing like magnesium 2 chloride or magnesium dichloride. Likewise, for sodium chloride, I didn't have to call it sodium monochloride or anything like that. I know this is a simple plus minus. So one of the pluses, one of the minuses. One thing is, if it's not obvious, a compound should be charge neutral. If it's not charge neutral, it's an ion. We can have molecular ions, it's just we're going to call it an ion. If we have a compound, it's going to be charge neutral. So we like to think of compounds being charge neutral. Aluminum is like 3 over, so it's beneath boron. It forms a 3+ cation. So aluminum salt's always 3+. Never 2+, never +1, always 3+ in compounds. Zinc and silver are 2 weird ones that the textbook and some examples that I've seen in like tests and some homework sets, they want us to know zinc is always +2 and silver is always +1. That those are the only 2 possible charge states for those metals. So those are just things that we'll come to know. See some examples that silver chloride's just AgCl, and that zinc chloride would be ZnCl2 because zinc would always be a +2. Ammonium is a collection of atoms in like a molecular form, so where we have a nitrogen bonded to 4 hydrogens overall with a net positive charge. We don't have to worry too much about what this looks like other than NH4+ is a molecular cation, and so this is ammonium. Hydronium is like protonated water. It's like H+ in water. So this is kind of sometimes just written H+, AQ. We'll talk about that more in chapter 4. But this is like a dissolved hydrogen cation in water. Then we have these 2 weird ones, Hg2 2+ and Hg2+. So notice that these cations here are kind of peculiar where we have 2 mercuries bonded together with a net 2+ charge. We call that one mercury 1. And then Hg2+, we call it one mercury with a Roman numeral sign. Now our transition metals, so all other transition metals are the name of the metal with the charge as a Roman numeral. So like if we look at like copper 2 is copper 2+. Manganese 5 is manganese 5+. Iron does this. Iron forms a 2+ and a 3+. Charge state commonly. We call one iron 2, the other one iron 3. So notice here, let's just end with this, that our transition metals, we have to use a Roman numeral charge system because we can't just look at the placement in the periodic table and get the right charge state. And they form a variety of different charge states. So because they form weird charge states, we use Roman numerals. The ones where we don't use Roman numerals, zinc and silver, because of whatever reason we're memorizing those ones, and then mercury is a little bit weird. So we memorize those weird ones with mercury. All other transition metals, we're using this Roman numeral charge system nomenclature. We'll get examples of this, and we'll see this in action as we get through some more notes on naming ionic compounds on Monday. Oh, sorry. Not on Monday, on Wednesday. We don't have class on Monday. I'll go back to the slide.